Debussy's Prelude to the Afternoon of a Faun. The opening flute solo and the harp all evoke a dream, creating the impression of a continuous blur. But if you listen closely, both the flute and harp are playing distinct notes, reminding us that the continuous blur is really made up of discrete notes. Thinking about discrete approximations to continuous random variables will help us in this lecture video, which is about computing the expected value of a continuous random variable. The central question we will address in this video is how to calculate the expected value of a continuous random variable. For example, here's a PDF. We have some sense that the center of mass is around here somewhere, but how do we find out where exactly that center of mass is? We can start by discretizing. Let's chop up the x-axis into lots of little slices, each of width delta x. For example, within this slice, x might range from 0.2 to 0.5, and if delta x is small enough, we can round all the values in this slice down to 0.2. Now we have essentially a discrete random variable that only takes on a few values, one value for each slice. So we can approximate the expected value as follows. For each slice, we pick a representative value x. Then we calculate the expected value as we did before, where we weight each possible value by its probability of happening, and then we sum over all the possible values. This is only an approximation because we are representing the entire slice from x to x plus delta x by a single representative value, x. Next, we're going to make another approximation. Instead of calculating the probability of each slice exactly, we can approximate the probability as the PDF times the width of that slice, delta x. The geometric intuition for this approximation is that we can represent the area under this PDF by rectangles, provided that the rectangles are sufficiently thin. So all of this so far is an approximation to the expected value of this continuous random variable. How can we make this approximation better? Well, we can slice up the x-axis more finely. In other words, we can take the limit as delta x goes to 0. And as delta x goes to 0, this sum becomes an integral, and delta x becomes dx. Remember that dx represents an infinitesimally small change. That's why it was called dx in the first place, to represent delta x in the limit as delta x goes to 0. So we'll take this to be the formula for the expected value of a continuous random variable. We integrate x times the PDF dx. Now, I want to take some time to compare the expected value formulas for discrete and continuous random variables. For discrete random variables, to calculate the expected value, we took the sum of x times the PMF over all possible values x. Now for continuous random variables, that sum becomes an integral over all possible values from minus infinity to infinity. The possible value x stays the same, and the PMF becomes the PDF times dx. Remember that the PMF tells us the probability the random variable equals x. For a PDF, this probability is always 0, but the PDF times dx roughly corresponds to the probability that the random variable is in some infinitesimally small slice around x. Next, let's look at the continuous version of another discrete formula that you've learned, lotus. Recall that lotus gives us a way to calculate the expected value of some function of x. It says that if we want to calculate the expected value of g of x, we still sum over all possible values x and their probabilities, but the probabilities now weight the values of g of x instead of just x. So, what do you think the continuous version of Lotus will look like? Again, the sum over x becomes an integral from minus infinity to plus infinity, the g of x stays the same, and the PMF becomes the PDF times dx. Now, these should not feel like four completely different formulas to you. You should develop intuition for how formulas for discrete random variables will translate to continuous random variables. Then, you'll only need to know the two formulas for discrete random variables, and the two corresponding formulas for continuous random variables will follow naturally. You've already learned an important strategy today for translating discrete formulas to continuous. You simply replace the sums by integrals and the PMFs by PDFs, and you sometimes have to add a dx.